lecture, I am going to continue from where I left off. For those of you who have the recording or listened to the first lecture, I had discussed the methods for calculating the reflectivity from an arbitrary scattering density profile, which is what reflectivity measures, for the non-magnetic case, by approximating this arbitrary scattering density profile with a series of slices with different scattering lengths, densities for each slice. And by making these slices as thin as necessary, you can approximate as accurately as you like the true scattering density profile in terms of this histogram. And so the problem was then to calculate the reflectivity rigorously from a series of such slices. And I discussed the methods, the iterative methods for doing this in the last lecture, and I'll just briefly go over that again here. So can I have the next slide? What one does usually is uses these parameterized box models to calculate the density profile. And then if you get a reasonable or a good fit, one uses a least squares fitting parameter to get the parameters of this model to fit the measured reflectivity. And this is also true for measurements of magnetic reflectivity. I should just say from my own experience, it is necessary to fit the reflectivity down to the smallest features, down to reflectivity values of 10 to the minus 6 or better, because subtle features in the density profile, scattering density profile, will not show up in just a crude fit to the reflectivity. So one needs to, if one wants to really extract the maximum information, one needs to fit the whole profile pretty well. Okay, can we have the next slide, please? So this is the basically the scheme that I discussed last time. You divide, you have these slices, each of which is assumed to be of a constant refractive index, which corresponds to a constant scattering length density. And if you have these layers, you can calculate you assume that there's a down and an up reflected beam from each interface, and and the wave number in the ith layer is given by the z component. The z component of that wave number is given by the z component of the wave number of the incident beam in free space, and then divided by subtracted from that is a constant appropriate to that ith layer, which essentially is the critical wave number for that layer squared divided by 4. And basically you have these different z components of the wave numbers in each layer, and of course the parallel components of the wave vectors are conserved from layer to layer, so we don't need to worry about that. Only the z components are different. And so the z component is ki downwards here and a negative ki upwards. We measure going into the into the layer as positive, this direction as positive, and this direction as negative. We have so then we can by using the boundary conditions that the wave function and its derivative have to be continuous at the interface, we can calculate the coefficients of these waves in terms of these waves, the one in the layer below. And if I can have the next slide, please. So if you write the neutron wave function in the ith layer, where I only consider the z component of the wave function, because as I said, the in-plane component factors out and is constant from layer to layer, so it disappears from the problem. and we're left basically with calculating solving a one-dimensional problem. So in the ith layer, we have this wave function, ai plus bi e to the minus I kiz. Matching boundary conditions, we can relate the two coefficients for the incident and the reflected wave to the corresponding coefficients in the next layer in terms of this 2 by 2 matrix, which is given here, and I won't go into the derivation. And so the reflection coefficient for the ith interface is given by simply the ratio of this coefficient to this coefficient. So it's just this ratio here. And if we apply this equation for all the interfaces successively, go on to the next one and the next one and the next one, we see that we can write ai minus 1 over bi minus 1 as the this matrix, this 2 by 2 column vector for ai bi can be iterated by making products of matrices from the ith layer down to the substrate of these 2 by 2 matrices, and then of course in the substrate there's no reflected wave. There's just the propagating wave into the substrate. So that actually enables you to solve the problem in terms of just this thing, and then you can eliminate that. So basically, we can write this product of matrices in terms of this 2 by 2 matrix, and so this 2 by 2 matrix is just this defined this way. Can I have the next slide, please? And I think the next slide, right? Yeah. So and then the reflection coefficient for the ith layer is simply bi minus 1 over ai minus 1. And that can be written in terms of the 2 by 2 matrix X of I in terms like this. And so the reflection from the top surface is simply R of 1 modulus squared. That's the expression for the reflectivity. And so it's given by x2 1 of 1 divided by x1 of 1 when I is equal to 1. That means taking the products of all the matrices from 1 to n. And so this involves the product of n 2 by 2 matrices, and this was all discussed in the book by Born and Wolf on optics. And it also yields the reflected and incident and reflected wave amplitudes in each layer. So if one is simply interested, if on the other hand one is simply interested in the reflectivity without worrying about what the amplitudes of the waves are in each layer, then we can proceed as follows. We can write the reflectivity again in this form, and as I said, it's given by this. But we recall that this matrix x of I is just m of I times xi plus 1, and so we can just replace that in the expression for Ri here, and we get this expression here. And then if you divide the numerator and the denominator by xii plus 1, you can see that using the definitions of reflectivity, we can write the reflectivity for the ith layer in terms of these coefficients and the reflectivity for the I plus 1th layer. So you get an iterative scheme whereby you can write R of I in terms of Ri plus 1, and R of I and R naught of I here, and these phase factors is just given by the ordinary Fresnel refraction coefficient for the ith interface. Can I have the next slide, please? So we can iterate this by starting from the nth interface to substrate and work backwards. We know that the reflectivity of n plus 1 below the substrate is 0. There's no reflected wave coming back at you from the substrate. And so if we iterate that equation back to R1, we get the reflectivity. And this is the method due to Peratt. And all these are discussed in the references I'll give you at the back of this lecture, and it'll be in my notes. So these are the two basic methods, the matrix method and the iterative method for calculating reflectivity from an arbitrary scattering density profile. And this is rigorously true. You can, at computational expense, you can make this as accurate as you like. And these are, with modern computers, this can be quite fast. And this is the methods that are often used to fit measured reflectivities to obtain some information about the sample. Can I have the next slide, please? Now, up to now, I've been talking about nuclear reflectivity, which is basically a scattering density profile just due to the nuclear scattering. If we want to add magnetic scattering and talk about magnetic reflectivity, then we have to recognize that the only component from the theory of magnetic scattering, which you've already had discussed in other lectures in this course, like the one by Colin Broholm at the beginning, we know that the only component of magnetization which scatters neutrons is the component of magnetization which is perpendicular to the wave vector transfer q. And so we can write that component as m perpendicular and project out the component parallel to the, this is the unit vector along q, and this is the magnetization vector. So actually, interestingly enough, since specular reflectivity corresponds to the vector q normal to the film, there is no contribution to specular reflectivity if the moments in the film are normal to the interface. So for perpendicular anisotropy, it's unfortunate, but you will not be able to measure those components of the magnetization with neutron specular reflectivity. Okay, let's go on to the next slide, please. So here's a vector diagram that expresses what I just said. Here's my incident wave vector, outgoing wave vector. Here's the wave vector q, which is normal to the surface if the angle of incidence and the angle of scattering are the same for specular reflectivity. Here's some general magnetization vector in the sample, in the film. And here is the component which is projected perpendicular to the wave vector q, so it's in the plane of the sample. And now furthermore, let's suppose that we're going to use polarized neutrons. Most magnetic reflectivity experiments with neutrons are done with polarized neutron beams. And let's suppose the neutron beams are polarized so that their spins are parallel to a certain direction, which is parallel to the surface. Then actually it turns out that it's the component of this in-plane magnetization projected along the direction of the neutron spin that is going to contribute to the reflectivity. So that is shown in the next slide. So here's how the argument goes. We now generalize the expression for the refractive index to the expression we had before involving the nuclear scattering, the density of nuclear scatterers. Here we're assuming for simplicity there's only one kind of nuclear scatterer with scattering length b, to including a magnetic term, which is given by the average or expectation value of this perpendicular component of the magnetization dotted with sigma, which is the operator, the Pauli spin operator for the neutron spin. And this is the gyromagnetic ratio of the neutron. This is the classical electron radius, or the Thomson scattering length of the electron. And this is the Bohr magneton. And so, depending on the direction of the neutron spin and the magnetization, this expectation value has to go in here. And from this value of the from this expression for the refractive index, you can see that the critical angle can be deduced the way we did before and involves this square root here. And so you can see that the critical angle actually depends on the direction of the neutron spin. So if it's parallel or anti-parallel to the magnetization, you will get different critical angles. So you will get a different, for instance, critical angle for reflection from a magnetic film for neutron spins in one direction compared to the other, and you'll get two different critical angles. and two different critical wave vectors also. Can we have the next slide, please? So as I've defined all the quantities, sigma was the Pauli spin operator. For the neutron spin, eigenvalues are plus and minus 1. Gamma is the gyromagnetic ratio, I'm sorry for the misspelling here, of the neutron equal to 1.91 and so forth. And I've defined these terms. Can I go into the next slide, please? Now, since we're working at specular reflectivity measures everything at relatively small wave vector transfer, so we're working close to the origin of reciprocal space, and the magnetic form factor that was defined in earlier lectures is essentially unity at small q, and can often be omitted from the expressions. So in principle, it's there because every atom that's contributing to the magnetic scattering has a distribution of magnetization whose Fourier transform is f of q. But when magnetization is present in general, we can write the scattering length density, which before was rho SL and just given by this expression here, for here, we now have to add to it plus or minus this m perpendicular sigma. The plus or minus term actually depends on this actually should be just a plus because the expectation value of sigma will determine whether the sign is plus or minus. And this subscript here refers to the nuclear density, and this is the neutron spin operator. So I will have to remove this in a future when I correct the lectures because this is just a plus here. The minus sign is taken care of with the sign of that. Can I have the next slide, please? So the simplest case, which is actually quite common, is when the magnetization lies in plane with in-plane anisotropy for the magnetic film, and the magnetic moments are collinear. That means you can arrange them to be parallel or anti-parallel to the neutron spins. So in this case, the neutron spins do not get flipped during the reflection process. We'll see that since you have m dot sigma, if you have a perpendicular component of sigma to m, there's a plus or minus quantum spin lowering or raising operator that's involved in that dot product, and that will cause the neutron spin to flip. And so perpendicular components, as we will see, will give you spin flip scattering. But in the case of neutrons parallel or anti-parallel to the neutron spins, if the magnetization is parallel or anti-parallel, the neutron spins will not get flipped. Then we simply have two different scattering length densities for the neutron spins, and they are given by this, where this is the magnetization profile, the average of the magnetization density as a function of depth into the film. And these are just constants, and this is the nuclear part. Can we go to the next slide, please? Now, for an unpolarized beam, of course, the magnetic reflectivity is just the reflectivities for each sign in the previous one, since both neutron spin polarizations will be present, and we just average them and add them to get the total reflectivity. So that's unpolarized neutron beams. Can I have the next slide, please? Now, for polarized neutron reflectivity, we get magnetizations that depend on whether your neutron spin is parallel to the magnetization or anti-parallel to the magnetization, and you can see that the reflectivities are different. And when you see different reflectivities like this, you know that you've got magnetization present. Otherwise, these two would be identical if there was no magnetization in the direction parallel to the neutron spin. So from fitting these two curves individually, using this generalized Peratt method or Born and Wolf method, we can extract the magnetization profiles as well as the nuclear density profiles. And then if you've got a magnetization which is perpendicular to the neutron spin, which is given by here. If the neutron spin is in this direction, and the magnetization happens to be in the perpendicular direction here, then you will get, in general, a spin flip component, which is shown in green here. And by analyzing that, we can measure the component of the magnetization perpendicular to the neutron spin. So you can actually measure this component of the magnetization as well as this component of the magnetization if the neutron spin is in one particular direction by using polarization analysis and measuring the spin flip and the non-spin flip components of the reflectivity profiles. Okay, can I go to the next slide, please? So this is just saying what I said, and in analyzing these magnetic reflectivities, you can either use the approximate master formula, which is not rigorous, but is sometimes useful in getting some idea of the magnetization profile, or the exact slicing methods that I've discussed before that. So either of those methods can be used to discuss the magnetic reflectivity. Can I go to the next slide, please? So we have to, in general, fit both curves, both plus and minus, and they will be different if a magnetization is present. And you can fit both of them and get, as I said, both the nuclear scattering length density as well as the magnetization profile. Can I have the next slide, please? So here's an example of a system. It turns out to be what's called an exchange bias system, which means it's a ferromagnet in contact with an antiferromagnetic film. And as a result, the coupling between the antiferromagnet and the ferromagnetic film shifts the hysteresis loop of the ferromagnet and gives you what's called exchange bias. So here you see the hysteresis loop, and you can see that that when you go below the ordering temperature of the antiferromagnet, by the way, in the paramagnetic case where the antiferromagnet hasn't ordered, you get the normal hysteresis loop. But once the antiferromagnet orders and the coupling sets in between the antiferromagnet and the ferromagnet, you get a shift of the center of this hysteresis loop and a big broadening of the hysteresis loop, and that is related to this phenomenon called exchange bias. Now, in these problems, it's often, to understand what's going on microscopically, it's important to know the magnetization density at the interface, the profile of the magnetization density. And it turns out that there's a ferromagnetic density profile even in the antiferromagnet that develops due to the so-called uncompensated spins in the antiferromagnet, which then couple to the ferromagnetic spins. And if I can have the next slide, please. This is an example of that same system measured on the magnetic neutron reflectometer at the spallation neutron source in Oak Ridge. And you can see that the plus and the minus reflectivities, that's with the neutron spin parallel and anti-parallel to the magnetization, which in this case is produced by saturating the magnetic film with an applied field in the exchange bias state, gives you a big difference between plus and minus, and these have been fitted individually, and so you can measure the magnetization profile and the nuclear profile individually. And I won't go into the details, but this black curve, essentially, this black curve indicates the nuclear density profile. Here's a capping layer of tantalum, and then the permalloy film, and a cobalt monoxide antiferromagnetic film, and here's the nuclear density in the black, and here's the magnetization density, which is mainly in the permalloy because this is an antiferromagnet, and there's a little magnetization into the antiferromagnet at the interface, but it is not in the bulk of the cobalt monoxide. And if you take an epitaxial film of the same thing, here's another case, then you can see the magnetization density is sharply cut off, and this is a different substrate, which is why the nuclear scattering density is different below the cobalt monoxide. But you can see the magnetization profile quite clearly here. And here there's a little spill into, there's a little magnetization induced in the cobalt monoxide. And here there's, it's sharply cut off right here. Can I have the next slide, please? And actually, let's go to the next slide because I want to show something. So it turns out that the exchange bias is caused by what's called moments that are pinned in the antiferromagnet. So when you saturate it with a field one way or the other, they stay pinned in that direction. And by coupling to the ferromagnet, they shift the hysteresis loop of the ferromagnet. Now, to measure the pinned components and the unpinned components separately, what you can show that when you reverse the field, the unpinned components reverse. So you get a plus and a minus here, but the pinned component stays the same. So if you measure the magnetization with the field saturated in one, with the saturating field in one direction and then the other, you can actually separate the unpinned and the pinned components. And that's shown in the previous slide. If you can go back to the previous slide, you can see that here, for example, is the measurement of the pinned density profile in the permalloy at the permalloy cobalt interface. And you can see that the pinned moments at the interface are oppositely coupled to the pinned moments in the ferromagnet permalloy. And at the permalloy cobalt interface, they're antiferromagnetically coupled to those. So that shows you the antiferromagnetic coupling at the interface. I won't go into the details of this. I'm just trying to show you the general principles of what you can deduce from these kinds of measurements. Let's go on to the next slide and the next one after that. We can skip this because I've already discussed this. Now, the thing I wanted to show here was that if you've got components of M which are in plane but perpendicular to the neutron spin, then you get, as I said, you get a spin flip contribution. And to treat this rigorously, you get a component of reflectivity which is R plus minus and R minus plus, which means you start off with a anti-parallel spin of the neutron to the magnetization, and you get a scattered component that's parallel to it, and vice versa. And to calculate these rigorously, with the slicing methods, we need to consider the neutron wave function in the ith layer as a spinner. So that means the neutron wave function is a two-component spinner where sigma can be +1 or -1, the Pauli spin operator. So this is the wave function for the neutron with a certain spin, sigma, and it has coefficients like, so this is really a two-component thing. And these are the coefficients of the wave function in the ith layer for the neutron with a particular spin sigma, and there's a corresponding one with the opposite spin. So this is the incident wave again in that layer, and this is the reflected wave. And again, we're only considering the z component of the wave function. The x and y components factor out, and they're the same for all the layers. If I can go to the next slide. So now you can proceed similarly, matching these two-component wave functions at each interface, and the result is you get 4x4 matrices instead of the 2x2 matrices to take into account both components of the neutron spin in the incident and reflected waves in each layer. So now you've got two components of spin coming in each layer and two components reflected. So you have these 4x4 matrices. And the plane wave solutions in each layer are the up and down spin solutions to a series of coupled Schrodinger equations with a spin-dependent potential, because now the refractive index in each layer will have a component which will flip the spin. And the details are given in a very nice paper by Chuck Marjak and his collaborators. And I'll refer you to that paper. It's given in the references at the end of this lecture. So how are we doing for time? I think 11:38. Okay, so we can continue to the next slide. And here is an example taken with Mike Fitzsimmons at Los Alamos on the Asterix reflectometer. Again, this is an exchange bias system consisting of cobalt on iron difluoride antiferromagnet. So what was done here was the field was applied, and so below the ordering temperature of the iron difluoride, so some of the pin moments were developed in the antiferromagnet parallel to the applied field, and then the field was removed and the sample was rotated by 90 degrees in the neutron beam, and the field applied along the new direction. So if the field is applied along the new direction and the moment is pinned in the perpendicular direction, you now have a component of the spin which is perpendicular to the new direction of the neutron spin, because the sample is now 90 degrees from where it was, and the moment is, some of the pin moments are pointing perpendicular. So you can measure that component of the moment with the spin flip scattering, which is shown here with the green curve, and by analyzing this, we can get the pinned component and another handle on the pinned component of the magnetization in the antiferromagnet up here. Okay, so that's enough of that. Let's go on. Let's skip this. We don't have time to discuss this. Okay, now for the remainder of this lecture, I want to get away from specular reflectivity and talk in general terms about what one can learn from off-specular scattering. So this is an analogy here is that if you've got a very smooth surface, like a lake without any ripples, you get the phenomenon of specular reflectivity. But if you can go on, if on the other hand, you've got some kind of roughness on the surface of the reflecting surface, in-plane fluctuations, in this case ripples on the water, you can see that the specular component is still there, but there's a diffuse component as well. And so roughness or in-plane fluctuations of the density profile will give rise to what's called an off-specular component or diffuse component of the reflectivity. And we'll see what kind of information can be extracted from that. Can we go to the next slide, please? So off-specular scattering can be due to either roughness at the interfaces or any kind of in-plane ordering or patterning. For instance, if you have magnetic stripes or some kind of magnetic pattern or some kind of ordering in the plane, you can get off-specular scattering. And that is what many instruments, which are either X-ray or neutron instruments at synchrotron and neutron sources around the world, are sometimes, there are specialized instruments to measure both the specular and the off-specular component. So let me talk about how you discuss off-specular scattering from the most simple case which you can think about, which is just what happens if you've got interface roughness. Can we go on to the next slide? Before I do that, let me just mention some of the applications for off-specular scattering. You can measure the morphology of surface and interface roughness. You can look at wetting layers and droplets on films. You can measure film growth exponents when films are growing. You can measure fluctuations on liquid surfaces of complex fluids, polymers, liquid metals, and so on. You can measure how islands grow on block copolymer films. You can measure pitting, corrosion, where you've got corrosion going on in a layer, magnetic roughness. We can study the morphology of magnetic domains in magnetic films. You can study nanodot arrays, and I'll show you examples of these. And these have applications in tribology, adhesion, electrodeposition, and so on. So there's a large number of areas of research where off-specular scattering can provide useful information. Can we go on to the next slide, please? So let's talk about roughness. So almost all real surfaces are rough, and if you go to the next pictures as we go in, if you keep going, these represent computer simulations of various kinds of roughness, which are generated by an algorithm called the Self-Affine Fractal algorithm, which has the capability of generating very realistic landscapes these are just colored and touched up to make them look like real landscapes. But if you look at electron micrograph pictures of real surfaces at the nanoscopic level, you can often fit them with this kind of model of roughness. Can we go to the next slide, please? So the mathematical algorithm paradigm that generates what's called self-affine fractal surfaces, that is defined as follows. So let's suppose delta z of r is a height fluctuation about the average surface. We can consider an average smooth surface at some point r, a two-dimensional vector r, in the two-dimensional plane of the surface. Now, the root mean square roughness, sigma, is defined by you take the square of this delta z of r, and you square it and you average it over the whole surface, and that's the mean square roughness, and you take the square root of that, and that's sigma. Now consider the quantity g of r, which is the average of the square of a height fluctuation, the height difference between 2 points separated by a vector r. And so you imagine a rod of length r thrown onto the surface, and you measure the height difference at its two ends, and you square that because it can be positive or negative, and you move this rod all over the surface and take the average of that square. And that's this mean square height difference function g of r. Now the algorithm that generates self-affine fractal surfaces is that g of r is postulated to be a power law that goes like some constant times the separation between these 2 points to some exponent, where this h is called the roughness exponent, or the self-affine fractal exponent, and is a number between 0 and 1. And notice that this goes like 2h because there's a square in here. Okay, so for real surfaces, however, this can't go on indefinitely, otherwise this thing would diverge, and all surfaces are finite, or the roughness correlations essentially die away as you go out in separation. And so there in general is a cutoff length, which we call C, and the way to introduce this cutoff length phenomenologically is to say that G of R is given by this expression. So you can see that when R is very large, this exponent, this is a kind of a stretched exponential function, which makes it a bit complicated, but you can see that when R is very large, this term vanishes, and G of R just becomes 2 sigma squared, as it should do, because now delta Z of R and delta Z of R plus R are uncorrelated, so you just get the sum of the mean square fluctuations of each of them, and it's just 2 sigma squared, since this is just what sigma squared is. But when R is small compared to the cutoff length, then you can expand this exponential, and by doing that, you actually obtain this form. And so you get the self-affine fractal form when R is much smaller than C. So it crosses over smoothly from the self-affine fractal form to a constant. And this implies that the height correlation function, which I call C of R, which is the correlation function between the height fluctuation at point R and point R plus R, this form implies that it's given by this stretched exponential function here, which kills this correlation at very large R and becomes just sigma squared when R is very small, and when it's essentially 0. Okay, can we go to the next? So here actually are some electron micrographs of real films that are produced by sorry, not electron micrographs. They are AFM pictures generated for certain surfaces, and you can see that they actually, by digitizing the image, they can actually measure this G of R function, and it does actually tend to go like a power law at small r and saturate, just like the algorithm that we discussed seems to indicate. And so basically, this kind of algorithm works reasonably well for many surfaces of interest. Can we go to the next slide, please? Now you can actually calculate the scattering from a surface defined in that way. As you know, the S of Q can be written as the modulus squared of the Fourier transform of rho of R. So this is S of Q, and you take the Fourier transform of rho of R, and if you take the modulus squared of that, that's S of Q, but we can write it also as a double integral with this thing times its complex conjugate here. So now we have this double integral, and you can see that basically we've got here like a correlation function between densities, and the Fourier transform of that correlation function is the S of Q. This is a very general form of S of Q, and will be true under all conditions, specular or off-specular. Now, if you assume that that the surface, the density of the material is constant below the surface and equal to rho naught, we can pull that out, and then the only thing that contributes to this correlation function is the fact that the surface, that material, this integral ends at the physical surface, and so when you do the integral over z, it ends at the top of the surface, which is given by some function z of xy, which defines the morphology of the surface, since this rough surface has a height function that is a function of x and y. And from this term, you get the minus z x prime y prime. So the z part of this triple sixfold integral can actually be pulled out here, and then we're left with the x and y part, so it's just the two-dimensional Fourier transform of that. And now, if these are random Gaussian fluctuations, which they generally are for the surface, we can use a theorem that says that this exponential, the average value of this exponential statistically, can be replaced by the exponential of the average value of the square of this quantity, which turns out to be this quantity here, which is related just to our function g of r, the mean height difference squared function, and qz. So once you know that and you plug that in there, then it's just the two-dimensional Fourier transform of that function that gives you S of Q. So finally, you can calculate, at least in the simple kinematic theory, and there's when you do the z integration, there's a factor because you're integrating over the qz, e to the I qz here. There's a 1 over qz factor that comes from each integration, and there are two of them, so you get qz squared. And then when you put this all together, you have that S of Q is equal to this function. This can be pulled out as the mean square roughness here from these two terms, and then the cross term in this will give you the height correlation function, which goes inside the integral, and you have a two-dimensional Fourier transform of this function of the separation between 2 points, which is the height correlation function. So you can see that the scattering now from these kinds of self-affine fractal exponents, self-affine fractal surfaces, can be expressed in terms of just this mathematically in terms of this height correlation function, which depends only on 3 exponents, which is the root mean square roughness sigma, the cutoff length xi, and the self-affine roughness exponent h. And so you can use 3 parameters to characterize or parameterize these surfaces and to fit this diffuse scattering data. And this has been done now fairly successfully for a large number of cases. Can I have the next slide, please? And as I said, that S of Q can be, if I go back to the previous slide, sorry, this S of Q, of course, this C of R function goes to 0 at infinity. So at infinity, this thing is still, this exponential function is still 1. And that will give me a delta function contribution to the two-dimensional Fourier transform. So I can pull that 1 out explicitly, and that just gives me delta QX, delta QR, which you will recognize as the specular component. And so I can pull out that 1 explicitly, and if I have the next slide, I can get the specular component in this approximation as just this part here with the delta functions, and the off-specular part with that 1 subtracted off is just this function, and this function does go to 0 as R goes to infinity, and so the two-dimensional Fourier transform is in general well behaved. And so for very small QZ, I can expand this exponential, and then I just get that the diffuse scattering is proportional to the two-dimensional Fourier transform of the height-height correlation function itself. Now, this is scattering in the kinematic Born approximation, and if you want to add to that particles on top of this rough surface with form factors F, L of Q at positions R sub L, then you simply add that to the scattering. If you assume they're uncorrelated with the substrate on which they're located, then you can get the scattering from a rough surface plus a bunch of nanoparticles by adding these two terms. Can I have the next slide, please? Now, the specular component is the limiting Born approximation expression for the reflectivity, and it should refer to the Fresnel reflectivity apart from this roughness factor e to the minus qz squared sigma squared. And to show that, we note that S of Q is simply the differential cross-section is simply S of Q. But from the definition of specular reflectivity, we have to calculate the reflected beam integrating over all solid angles into the detector and divide by the fraction of the incident beam that was intercepting the substrate, and that's given by this expression here. And so when you integrate the delta function in this expression, which is in the specular part over solid angles, you do that by expressing the solid angle d omega into the detector in terms of dqx and dqy, and a Jacobian factor, which is k naught squared sine alpha. And then you find that the expression for the reflectivity, you can trivially integrate over the delta functions in qx and qy, and you get this expression, which is in fact the limiting expression from the Fresnel reflectivity. And if you put in the roughness term, it is in fact boils down to the kinematic or Born approximation expression to the specular reflectivity from a rough surface. It doesn't work near the critical angle, and it does work far away from for large scattering angles. Okay, can I have the next slide, please? Here's an example of another rough surface, electron micrograph picture. And again, you can see this GR function that's measured with either STM or AFM. And again, you can see it starts off as a power law and saturates. So you can measure the... And when you compare these kinds of curves taken in with measured with AFM or STM with the same parameters you get from analyzing diffuse scattering measurements, you in general find pretty good agreement. Okay, next slide, please. And here is a composite picture which shows the specular reflectivity from a rough surface. It's a rough glass surface here, calculations from a rough glass surface. And at each QZ, you can imagine a rocking curve done, which measures the diffuse scattering component. Now you can see these peaks in the off-specular scattering, which are not explained by the expressions that I gave in the up to now. These are called Yoneda peaks because they were first discovered by Yoneda, and they occur when the angle of incidence or the angle of scattering is exactly equal, mixed with the surface exactly the critical angle. And this is qualitatively, this can be explained by the fact that at these angles, the incident and the reflected beam are exactly in phase, so the electric field at the surface builds up to twice its value, and so the intensity for the diffuse scattering is multiplied by a factor of 4, and so it builds up at those. Remember, this is a logarithmic scale, so it builds up at these points by a factor of 4, and the quantitative explanation of this kind of peak or this kind of shape of the diffuse scattering can only be explained in what's called the distorted wave-borne approximation, which I will just discuss briefly at the end. I think we're coming very close to the end. Let's go on. I'll just show you the generalization to a multi-layer structure. If you've got a multi-layer structure, you can have roughness in each interface, and this roughness can be correlated with the roughness below, or uncorrelated, or partially correlated. In fact, for most multilayers or thin films, the two surfaces are very, in general, usually highly, surprisingly well correlated. And so there, you have to consider now the height fluctuation from this interface and its correlation with the height fluctuation at an interface, a different interface at a distance r, and you have to consider that kind of correlation function as well. And when you take these correlation functions into account, you get the expressions in the next view graph slide, where you can, this is the full expression here, where this is a sum of all interfaces in this multi-layer system. These are the mean square roughness of each of these interfaces. This is the mean z positions of the interfaces. And then this is the, to get the off-specular scattering, you have to take the two-dimensional Fourier transform of all these correlation functions. This one, for instance, is just the nuclear part and is given by this is the height correlation function between interfaces I and J, separated by distance r, multiplied by qz squared as before. And this is the scattering length density contrast across interface I and interface J. And you multiply these two, and you multiply by this correlation function, height correlation function between these two interfaces, and you put it in this, and that is the purely nuclear part to the scattering from a multi-layer with rough interfaces. But if you've got magnetic scattering as well, then you have to consider the correlations between the magnetic magnetization in each layer, the ith layer and the jth layer, and the dot product with the neutron spin, and the contrast across each layer, of course, and then the cross correlation between the height fluctuation, the nuclear scattering, and the magnetic scattering in each layer, and then the purely magnetic correlation. So it gets very complicated, and if you go to the next slide, let me not go into the details, but let me just point out that if you go back, sorry, can you go back to the previous slide? If the correlation function between layers, if the layers are highly correlated, then this function actually tends to be independent of whether you're correlating a layer with itself or with a layer above, because they all correlated together. And so this function tends to become independent of I and j in the limit of perfect correlation. And then it's just the same as if we forget the magnetic parts now, it's the same as the scattering from a single layer, but with these phase factors in there. And you can see that these phase factors will combine to give me coherent constructive interference at QZ equal to the multilayer Bragg peaks. If these layers are correspond to bilayers periodically repeated. And so if I go to the next slide, you will get diffuse scattering, which is quite strong whenever QZ is equal to the Bragg peak. So you get streaks of diffuse scattering through the multilayer Bragg peaks, and that's an indication of correlated roughness. Now, I think I've reached the end of my allocated lecture time, so I'm going to quit here, but I'll just come to the end. I may skip the last few slides. Can we go on to the next slide? So I was going to talk about magnetic diffuse scattering and magnetic roughness, but I don't have time to go into that here. I would suggest you can go and look at the papers on this that we published in Physical Review, and look at the slides, which will be in PowerPoint form or in PDF form on the website. And let's go on. Let's just skip these, and skip these, and skip these. And then I should just mention that a large component to magnetic diffuse scattering is in fact due to domains that you get. Like this is a picture of domains. Let's say we have one spin here and another spin here, another kind of spin, let's say plus here and minus here. The simplest picture of a domain system on a magnetic film or a magnetic multilayer. And so if you go on, if you look at the diffuse scattering from this domain structure, then if you go back a couple of slides, keep going back, please keep going. Go back. So here, what this domain scattering will give you is the Fourier transform of what's called the Debye correlation function, and this is defined as follows. If you throw a stick of length r onto this surface and you ask for the probability that one end of that stick is in one kind of domain and the other end is in a different domain, then that defines a correlation function gamma ij of r. You average that over all possible orientations of the stick over the surface, you get this function gamma of r. And you take its Fourier transform, and that is the diffuse magnetic scattering. So let's go back to those slides. Keep going. And keep going. And you find that basically you have the Fourier transform of this function that you need. And if you assume sort of random domains on the surface given by sort of not striped domains, if you get striped domains, then you get very nice peaks from this. But if you get just random domains, then you can define this function, as Debye showed a long time ago for random porous media, is given by an exponential function, or Poisson statistics is the probability you'll encounter another domain wall as you keep going along the direction r. And the Fourier transform in two dimensions of this correlation function is a Lorentzian to the 3/2 power. So that's the sort of form you should get for diffuse scattering from magnetic domains. And then, of course, if it's in a multilayer and it's correlated, the domains are correlated above each other, you get this domain scattering will be in streaks through the magnetic Bragg peaks, and so forth. So I think I've tried to outline for you the broad features of diffuse scattering from roughness, magnetic scattering, diffuse scattering from magnetic domains, and how they fit together in multi-layers. I haven't been able to go into the details very much, but it's sort of in these notes, and if you read the papers at the which are given with these lecture notes, if you read the references, you can get more information. Let me just skip to the end here. Let's skip this. Oh, just go back to that slide for 1 second. I just want to point out. So this is an iron chromium multilayer, and this streak of diffuse scattering here is through the antiferromagnetic Bragg point, is due to the antiferromagnetically correlated in the z direction domain structure in the layers. And so that's the domain scattering, and it's strongly correlated antiferromagnetically this way, this way, this way, this way as you go up. So it shows up as a streak through the antiferromagnetic Bragg peak. Let's keep going. So that's the same thing again for an iron chromium system. And from the detailed analysis of this in-plane diffuse scattering, you can see peaks which correspond to this function gamma bar, which will give you information about the domain sizes and their separation, which are sort of shown here by fitting this data. Let's go on. And you can also study magnetic nanostructures, periodic pattern nanostructures. In this case, you will get a periodic structure in 2 dimensions, and the Fourier transform of that will be rods of scattering through the 2-dimensional reciprocal lattice of this periodic structure. So to look at these rods will give you information about this pattern structure. Again, I don't have time to go into this in detail, but you can read the reference in the original papers. Just keep going. In this paper, we measured the rod scattering from a pattern structure which corresponded to a permalloy film which was magnetized, but with a series of periodic holes in it, or anti-dots, which were arranged in a periodic square lattice of size 2 microns. And by doing grazing incident scattering, we were able to figure out the magnetization. Keep going. So the magnetization pattern, which you can verify by micromagnetic calculations, was verified for this kind of pattern of magnetization as well. And its details are given in this paper. Let's just keep going, keep going, keep going, keep going, keep going. And the final remark I want to make is that if you want to go beyond the Born approximation, then you can use what's called the distorted wave Born approximation, which is discussed in one of the references at the given with this lecture. And the net result of using this approximation is to replace the sum of the incident and reflected waves in the second medium by a transmitted wave. And so what happens is that the diffuse scattering for a single interface gets multiplied by these 2 factors, which are the Fresnel transmission coefficients at grazing incidence angle, angle of incidence alpha, and outgoing angle of scattering beta. The Fresnel transmission coefficients T alpha and T beta modulus squared multiply the expression we had before, and you simply replace QZ by QZ in the medium, which is slightly different, as we explained before, due to refraction effects. So for multilayers, this distorted wave Born approximation gets more complicated, but it has been done, and it works near the critical angle, and therefore is valid in most regions, and is now commonly used to analyze diffuse scattering from multilayers and single films if you want to discuss the diffuse scattering near the surface. And it's also used to discuss what's called GSACs or GSANS experiments, where you come in at grazing incidence and look at the scattering in an area detector due to the in-plane structure of nanoparticles or patterned surfaces in the plane of the surface. So that kind of experiment is being done more and more, and there are instruments devoted to that at synchrotrons and in some neutron facilities. So I would suggest, just to make you aware of that, that in general, the analysis of that kind of data, since you're coming at grazing incidence, basically the DWBA is a way of taking into account the effect of the reflected wave, which is always there. So you have scattering not just from the incident wave, but also from the outgoing reflected wave, specularly reflected wave, and the diffuse scattering pattern now is more complicated because two of these waves contribute and there's phase interferences between those amplitudes. Okay, so that essentially completes my lecture, and I will give you at the end a list of references. If you could switch to the next slide. Here are some references for further reading. These are the articles by Peratt that I referred to for the Peratt method. Born and Wolf's treatise on principles of optics has the matrix method in it. The Polarized Neutron Reflectometry for specular magnetic reflectometry involving the full spin flip terms is given in this article by Marjak and co-authors. And the diffuse scattering method that I discussed is given in this physical review article in great detail. And if you can go to the next slide. If you want to see the treatment for multiple interfaces, there are many papers discussing that, and I've listed some of them here. So thank you very much for your attention. I will put these lecture notes up on the website for this course, and you can refer to them in the future. And thank you for your attention. I think we're done.